Welcome to Module 1. Module 1 covers Chapter 1 and Chapter 2 from your textbook. This is module objectives. In this module, we will define some statistics terms, and I will need you to pay close attention to these terms because later throughout the semester, you will need to understand those terms very carefully. Otherwise, you will be stuck when you are supposed to use SPSS. So we will touch a little bit about defining validity, reliability, distribution, mean, median, and mode. We will differentiate between samples and populations. We will talk about standard deviation, deviance, variance, confidence intervals, type 1 and type 2 error, and we will talk a little bit about significance testing. As an introduction, let's define some terms. First of all, variable. When we start reading statistics, when we start reading a research article, we come across different variables. So we need to know the definitions of these terms. This is very important. So variable is a feature or condition that can vary or take on different values across people. For example, body weight, height, age, fasting blood glucose level, cholesterol level, or other lipid profile level. Those are all variables because they can vary across people. My weight can vary from your weight. My height can vary from your height or your weight. My BMI can vary from your BMI. And those variables, BMI, height, weight, age, can take on different values. So we call them variables. And variables can be categorized into different groups, and we will talk about that in a few slides. So data is another term. It's very important. Um, some people call it data or data. So data is plural, and the singular form of data is datum. So data is the measurements, observations we record for a variable. We call that data. Data set, it's a group or collection of all those measurements or observations. Imagine an Excel sheet or a spreadsheet where we have different rows, different columns, and each cell in Excel file or spreadsheet takes on different values, different uh, features or conditions. So overall, that Excel file or spreadsheet, it's called dataset. Each row represents different people, different observations, different measurements, and the columns are variable, for example, depending on our dataset type. And the datum, as I said, is the singular form of data. It refers to one individual measurement or individual observation. Um, Remember, there are different terms referring to datum. For example, score, raw score, observation, individual measurement. These are all mean datum, which is a singular form of data. There are two main types of data analysis. There are two types of methods to analyze data: quantitative methods or numbers, and qualitative methods or words. So let's say we want to try test theories using numbers. Our testing method is quantitative. On the other hand, if we want to test some theories using language, using word like magazine articles, conversations, newspapers, media broadcasts, those are called qualitative methods. The focus of this course is about quantitative methods. So we will deal with numbers. We will deal with words, but we will try to kind of like assign numbers to them in order for us to analyze them. So we will talk about quantitative methods in this class. Let's do this together. So check yourself, qualitative or quantitative. The age of your car. So the age is a numeric, it's a number. So it's quantitative. The number of hairs on your knuckle. Again, it's number, it's numeric, it's kind of continuous variable. It's quantitative. The softness of a cat. Can we measure it? Can we measure the softness of a cat? Can we assign numbers to it? Actually, no. So it's qualitative. The color of the sky. It is blue, it is black, it is red, it is yellow, whatever. It's qualitative. It's not quantitative. The number of pennies in your pocket. Again, the number, it's numeric, it's continuous variable, so it's quantitative. This is the research process. First, we start with an initial observation to come up with a research question. For example, out there in the real world, uh, there are a bunch of data, and we do an initial observation, and we come up with a research question. Or we read research articles and find a gap, and we want to fill that gap. So we come up with a research question. We develop theory after initial observation. From theory, we generate hypotheses. From hypotheses, we generate predictions. From predictions, we collect data to test those predictions, and we analyze data. And then we can come back to theory. We can develop new theories, or we can confirm the existing theory. This is the overall process of the research. So the first step in the research process is initial observation. As I said, we can observe the real world or read other research. We need to test the concept. In order to test the concept, we need to collect data. We need to collect data to see whether your hunch is correct. And to do this, we need to define variables. So here, after generating hypotheses, we need to identify variables. So we need to define our variables, the variables we want to measure. The variables are those individual measurements, are those individual observations, are, are the features and conditions that can take on different values. And they can differ across entities or time. The second step is from theory to generating predictions. So generating and testing theories. Let's define theories and hypotheses. So theories is hypothesized general principle or set of principles that explain known findings about a topic and from which new hypotheses can be generated. And hypothesis is a prediction from a theory. For example, the number of people turning up for a reality TV audition that have narcissistic personality disorder will be higher than the general level 1%, for instance, in the population. So this is a hypothesis. We generated a prediction from a theory. The theory is the people turning up for a reality TV audition that have narcissistic personality disorder will be higher. That's a theory. But we hypothesize that that number will be around 1%. So that's a hypothesis which is generated from a theory. Falsification, this is very important, and this is very bad practice. Falsification is the act of disproving a theory or hypothesis. It is the act of deliberately misrepresenting something. That is falsification, and it is a really bad practice. So, as I said, variables, which are the features or conditions that take on different values, um, and they can differ across people, across entities, or time, we can categorize variables into different groups. There are multiple ways of categorizing variables. One way is we categorize variable into two main groups: independent variable or dependent variable. And there are other names referring to independent variable. For example, the proposed cause, a predictor variable, a manipulated variable. These are all referred to independent variable. On the other hand, dependent variable are the variables that are an outcome, that are the proposed effect, measured, not manipulated. These are dependent variable. For example, let's say our hypothesis is cooking demonstrations help kids develop healthier eating habits. This is our hypothesis. Let's identify dependent variable and independent variable from this hypothesis. So, dependent variable, we can infer from the name, it is it is a variable that depends on something else. So healthier eating habits depends on cooking demonstrations. So dependent variable in this example will be healthier eating habits. Independent variable will be cooking demonstrations. It is totally independent from other variables. We have four levels of measurement. This is another way of categorizing variables. This is another way of looking at variables. So one way is categorizing variables into two main groups, independent or dependent variable. But regarding the level of measurement, we can categorize variables into four main groups. Variables can be nominal variables, ordinal variables, interval variables, or ratio variable. So let's start with nominal variables. Nominal variables can be nominal variable or binary variable. Binary variable are variables that they have only two categories. For example, dead or alive, healthy or ill. That's a binary variable. Success or failure, head or tail in a coin, for example. This is a binary variable. There are only two categories. Nominal variables are similar to binary variables, but the only difference is there are more than two categories. For example, whether someone is an omnivore, vegetarian, vegan, or fruitarian. This is a nominal variable. It is a categorical variable. And remember, binary variable, nominal variable, and ordinal variable, they are all falling under categorical variable. Categorical variables are entities are divided into distinct categories. The next level of measurement is ordinal variable. Ordinal variable is very similar to nominal variable, but the difference is there is a logical order. For example, whether people got a fail, a pass, a merit, or a distinction in their exam. There is ordinal there. Or education level. It's less than high school, above high school, college graduate, above college. That's a categorical variable, right? But there is a logical order there. High school graduate is higher than less than high school, or above college is greater than, is higher than high school, for example. Interval variable and ratio variables are continuous variables. These are numeric variables. In interval variable, there are equal intervals on the variable represent equal differences. For example, the difference between 6 and 8 is the same as the difference between 13 and 15, which is 2. Ratio variable, it's very similar to interval variable, but the zero has a meaning in ratio variable. That's the main difference between ratio variable and interval variable. When we say zero means nothing in ratio variable. For example, body weight equals zero. It means absence, it means nothing. But in interval variable, for example, body temperature is 0 Celsius. Let's say room temperature is 0 Celsius. Um, that zero means something. It doesn't mean absence. So that's the main difference between interval variable and ratio variable. So this is also the level of measurement. This figure shows how important each level of measurement is. So ratio level of measurement, it's much better to utilize in research articles, and I will mention why. Why is that? So nominal level of measurement is the lowest of the four levels. There is no order. It's quality, not quantity. Categories must be unorderable. For example, the type of car you drive, male or female. Ordinal, the categories are orderable by size, cost, height, importance, or complexity. And we have unequal intervals in ordinal level. In interval level, we have equal intervals. In ratio, we have equal intervals. But in ordinal, there is an unequal interval. Remember, if numbers are used for categories, it is called a metric ordinal scale. But this is very important. Adding up those numbers doesn't have any meaning. For example, education level is an ordinal level, right? I can assign numbers to each level of education level. I can say less than high school, I would assign 1. High school 2. Above high school is 3. College graduate is 4, and etc. I can assign numbers for those categories, and that's called metric ordinal scale. But can I add up those numbers? Does it mean anything? It doesn't mean anything. It is used for some self ratings. For example, IQ scores. It's an ordinal level of measurement. In interval level, the categories are orderable. The distances between intervals of the scale are numerically equal, may or may not contain a zero. Man-made scales are all at the interval level of measurement. For example, we have different scales. We have different types of surveys, like self-efficacy, self-esteem, or Likert scale. Those are scales that are in interval level of measurement. Unless zero on the scale means an absence of the entity measured, absolute temperature scale. So temperature with the Celsius scale, which has an arbitrarily defined 0 point, like body temperature, these are interval level of measurement. Ratio is the highest form of measurement. Numbers are in order. There are equal intervals between numbers. Two values added together produce a meaningful value. Always contains a zero. Zero really means none of the quality that is being measured. So there's an exception regarding temperature. If the temperature is in the Kelvin scale, the 0 Kelvin scale is called absolute zero, which means there is no heat. So that is ratio level of measurement. That's an exception. There are other examples, weight, length, volume, those are ratio level of measurement. Statistical tests chosen on the basis of the level of measurement. So we will use this later whenever we try to analyze our data. Depending on the level of measurement, we will choose different statistical tests. For that, we have parametric tests and non-parametric tests. Parametric tests are for ratio and interval measures. Non-parametric tests are for ordinal and nominal measures. So, for example, for parametric tests are regression analysis, correlational analysis, t-tests, pair sample t-test, ANOVA, MANOVA, and COVA. Those are parametric tests. For non-parametric tests are like Mann-Whitney U-test, Wilcoxon signed rank test. Those are non-parametric tests. Spearman correlation, it's non-parametric test. Um, we have chi-square. No, it's a non-parametric test, which is for ordinal and nominal measures. One should use the highest level of measurement possible. Why? What do you think? So the ratio level of measurement, whenever we use the ratio level of measurement, we have more freedom of choosing our statistical test first. Second of all, we can convert our ratio variable into a categorical variable, but we cannot do that, vice versa. I mean, we cannot convert a categorical variable to a ratio variable. So we have more freedom when using ratio level of measurement. Measurement error occurs always, anytime. Measurement error is defined as the discrepancy between the actual value we are trying to measure and the number we use to represent that value. That is called measurement error. For example, you in reality weigh 80 kilograms. You stand on your bathroom scales and they say 83 kilograms. So the measurement error here is 3 kilograms. Remember, there is always measurement error. Our approach is to minimize the measurement error as much as we can. You know, we try our best to minimize that measurement error, but there is always a measurement error, and we cannot ignore it. We cannot prevent it. Measurement error, this is also called variation. Remember that. Measurement error is also called variation. It can be random or systematic. Systematic measurement error is easier to correct than random error, and it can occur in both direct and indirect measurements. Can you provide some examples for direct and indirect measurements? So direct measurements are like measuring our body weight, measuring our height, age, fasting blood glucose level. Those are direct measurements. Indirect measurements are like Measuring total energy expenditure, that's an indirect measurement. Measuring our kidney health by measuring eGFR, that's an indirect measurement. So for indirect measurements, we use a different measurement. We use different formulas to get an idea about a different thing. For example, like we measure GFR to get an idea about the kidney health. That's an indirect measurement. We measure our VO2 divided by CO2, um, the other way. VCO2 divided by VO2. That's an indirect measurement of total energy expenditure. So there is always measurement error, whether it is direct or indirect measurement. Validity and reliability are very important concepts. So validity refers to whether an instrument measures what it set out to measure. So when we say validity testing, we mean validating use of an instrument for a specific group or purpose rather than the instrument itself. That is validity testing. By validity testing, we validate use of an instrument for a specific group or purpose. For example, we try to validate a scale or survey for a specific group of people. That's validity testing, not the instrument itself. So just remember, validity is whether an instrument measures what it set out to measure. We will never have a completely valid instrument, but can aim for determining the degree of validity and having an instrument that is as valid as possible. There are different types of validity. We have content validity. That is the evidence that the content of a test corresponds to the content of the construct it was designed to cover. For example, the self-efficacy survey should measure self-efficacy. That's content validity. IQ scale should measure IQ, not body weight. That's content validity. Ecological validity, it refers to generalizability of our measurement, of instrument, of our results of a study. Whether it allows us to infer it to real world conditions. That's ecological validity. We have criterion validity, which can be predictive validity or concurrent validity. So predictive validity is predicting future outcomes. For example, test scores predicting job success. That's a predictive validity. Concurrent validity, it's correlating with a criterion measured at the same time. For example, a new IQ test matching an existing one. That's concurrent validity. Reliability is the ability of the measure to produce the same results under the same conditions. For example, I would say my bathroom scale is reliable whenever it measures my body weight accurately over time, over and over again, today, tomorrow, and the day after tomorrow. It measures, I weigh 80 kilograms, my bathroom scale measures that every day, for example. That's reliable. I put in my key in my car and turn it, the engine starts. My car is reliable. Test retest reliability is the ability of a measure to produce consistent results when the same entities are tested at two different points in time. For example, let's say we have a 10-week program. We have 24 month program and we are measuring self-efficacy. We are using the same person at baseline at 24 months endpoint, and we are trying to measure self-efficacy of people. So we can do test retest reliability in order to measure the ability of our measure to produce consistent result over time. Which would be the best for any study? Reliable, not valid, low validity, low reliability, not reliable, not valid, both reliable and valid. Of course, both reliable and valid. There are different types of research. Research can be correlational, which is kind of showing relationship between different variables. Research can be cross-sectional. This term implies that data come from people at different age points with different people representing each age point. So cross-sectional studies, we are trying to measure something at one cross section of time, at just one point. That's cross-sectional research. Research can be experimental. Remember, there are more than these types of research, but these are the main ones. Experimental research is a one or more variable is systematically manipulated to see their effect on an outcome variable. And statements can be made about cause and effect in experimental research. So let's do this example together. Of 250 people measured, is there a relationship between high fructose corn syrup and obesity? So here it says, is there a relationship? So this is a correlational. The next one is saying how many consume 50 gram of high fructose corn syrup each day. This is cross-sectional. And the other one is comparing two groups of people, one intervention group and another control group. So that's experimental research. Which is more natural? Correlational, experimental, or cross-sectional? Correlational research is more natural, which allows you to infer causation. Cause and effect is coming from experimental research. These are the criteria for cause and effect. There are three terms, three criteria. And remember, we have confounding variables in experimental research, and we need to try our best to minimize, to kind of rule out the effects of confounding variable. For example, the relationship between high fructose corn syrup consumption and obesity can be confounded by bacon intake, genetic factors, and other variables. So we need to try our best to rule out confounds. In experimental conditions, we have between subject, independent, or between group. These are different entities in experimental conditions. In repeated measures, we have within subject measures. The same entities take part in all experimental conditions. For example, in longitudinal studies, let's say 24 months program, nutrition program, we are measuring self-efficacy of 30 people enrolled in our program for 24 months. So we will analyze within subject actually in that case. We are trying to see if there is any difference in self-efficacy before enrolling in the program and after 24 months of enrollment. So that's repeated measures, that's within subject. So I already talked about this. So measurement error is kind of a variation, and it can be systematic variation or unsystematic variation. Randomization in experimental research minimizes unsystematic variation. And the final step in research process is analyzing data. First of all, when we start analyzing data, we need to create some plots or graphs. It's also known as histograms. We need to have a frequency distribution. A graph plotting values of observations on the horizontal axis with a bar showing how many times each value occurred in the dataset. And we have normal distribution, which is a bell shape. This is a normal distribution. X-axis is our scores, and y-axis is the frequency of each score in the dataset. And whenever we plot this dataset, it shows a normal distribution. It's a bell-shaped distribution. It is symmetrical around the center. In a bell-shaped or normal distribution, our central tendency, we will talk about that later, our mean, median, and mode are all equal. Left side is a mirror image of the right side. That's the concept of symmetry. That's in ideal world. Normal distribution is an ideal world. But in reality, most of the time, we see skewness and kurtosis. So skew is the symmetry of the distribution. We have positive skew and negative skew. Also, we have kurtosis, which is the heaviness of the tails. So for example, here, on the left side, we have positive skew. On the right side, we have negative skew. The positive skew, in positive skew, the tails are pointing to the right side of the graph or towards the positive values. In negative skew, the tail of the frequency distribution are pointing to negative values. So any curve that is not symmetrical is referred to as skewed or asymmetrical. Positively skewed, largest portion of data is below the mean, and in negatively skewed, largest portion of data is above the mean. Mean, median, and mode are not equal, as we can see from this figure. In positively skewed and in negatively skewed, none of those central tendency values are not same. So kurtosis shows the degree of peakedness of the curve. It is related to the spread or variance of scores. Leptokurtic, it is extremely peaked curve. Mesokurtic is intermediate degree of kurtosis, and platykurtic is relatively flat curve. So here is the picture of leptokurtic and platykurtic. Central tendency refers to a single value summarizing a dataset's center or typical value. So we have three central tendency. Mode is the most frequent score. We can have bimodal or multimodal, having two modes or having several modes. So unimodal is it occurs when there is only one mode, the most frequent data in our data set. Bimodal, we have two humps. Trimodal, we have three humps. And this is the pictures of bimodal and multimodal. The median is another central tendency. Again, remember, central tendency is a single value summarizing the dataset, summarizing the center of the dataset. In order to to get median, first we need to order our data set from smallest value to the largest value. And then the midpoint will be our median. When the data contain an even number of scores, the median is the average of the middle two values. The mean is the most important value of central tendency. It is the sum of scores divided by the number of scores. So we have an example here. Number of friends of 11 Facebook users. So if we want to get the mean of number of friends of 11 Facebook users, we need to add up the number of friends of all those 11 users and then divide that by 11, which gives us 95. There's a disadvantage of the mean, which is it can be influenced by extreme scores. It is also affected by skewed distributions and can be used only with interval or ratio data. The range shows dispersion. So central tendency shows the center of the data set. But there are other values that shows how much our data set is spread out or how much is dispersed. So the range is one of them. The smallest score subtracted from the largest score. So in our Facebook example, the range is 212 just by subtracting the smallest value from the largest value. Quartiles, it's kind of a range, but quartiles are more common than range. I have seen quartiles in many research articles. So in order to get quartiles, first we need to order our data set, and then we need to divide our data set into four equal parts. And each part is a quartile. So we will have lower quartile, median or second quartile, and upper quartile. There's another term here. It's called interquartile range, which is the difference between upper quartile and lower quartile. So remember, let's say we ordered our data, we have ordered it, and then we identified quartiles, which is the midpoint. So for example, the lower quartile is the midpoint of the lower part of the ordered data. The upper quartile is the midpoint of the upper part of the data. And the median is the second quartile. Deviance is another way of showing the spread of scores by looking at how different each score is from the center of a distribution. For example, the mean. So the deviance is each data point minus X bar, which is the mean of our data set. That's deviance. And we can also add up all those deviances and get total deviance. Sum of squared errors, or SS, we need to add up all those deviances and then square it. That's sum of squared errors. The variance is sum of squared errors divided by n minus 1. N is the number of data points. So in our Facebook example, we had 11 Facebook users. So n minus 1 will be 10. And the SS is sum of squared errors. That gives us variance. So sum of squared errors indicates the total dispersion or total deviance of scores from the mean. Its size is dependent on the number of scores in the data. That's obvious because it is n minus 1. Its size is dependent on the number of scores in the data. It is more useful to work with the average dispersion, known as the variance, than sum of squared errors alone. The variance gives us a measure in units squared. So in our Facebook example, we would have to say that the average error in our data was 3,224.6 frames squared. It doesn't, it means something, but it is hard to understand. It is hard to interpret that data, that value. So this problem is solved by taking the square root of the variance, which is known as the standard deviation. So standard deviation is 56.79. This number, this value shows that the number of friends among 11 Facebook users is 56 friends away from the mean. Whenever we have the same mean but different standard deviation, it shows that in larger standard deviation, the data is more spread out. The variance and standard deviation tell us about the shape of the distribution of scores. If the mean represents the data well, then most of the scores will cluster close to the mean, and the resulting standard deviation is small relative to the mean. When the mean is a worse representation of the data, the scores cluster more widely around the mean, and the standard deviation is larger. So here are the important things to remember. The sum of squares, variance, and standard deviation represent the same thing. They represent the fit of the mean to the data. They represent the variability in the data. How well the mean represents the observed data. They all represent error. This is normal probability distribution. It is another way to think about frequency distribution. In this case, instead of having raw scores and raw frequencies, we have probability instead. So the area under the curve equals 1, and it shows the probability distribution of, it's showing like what's how likely is it is that a score would occur. This is all about the normal probability distribution. We have z-scores. Z-scores measures how many standard deviations a data point is away from the mean of a dataset, indicating its relative position. Z-scores standardize a score with respect to other scores in the group. It's kind of helping us compare samples, different groups of people, different data scores with each other by standardizing scores. So in z-score, the mean is 0 and the standard deviation is 1. And we have positive z-scores and negative z-scores. Z-scores expresses a score in terms of how many standard deviation it is away from the mean. So 1.96, this is our z-score, cuts off the top 2.5% of the distribution. The negative 1.96 cuts off the bottom 2.5% of the distribution. So positive z-score means above mean, negative z-scores means below the mean. So 95% of z-scores lie between minus 1.96 and 1.96, and etc. We have two types of tests. We have one-tail test and two-tail tests. Whenever we have one-tail test, the probability is 0.05. When we have two-tailed test, the probability is 0.025. So this is the concept of probability density function of a normal distribution. And the final step is to report our data in order to publish it in scientific journals. Chapter 2 is about this spine of statistics. So in this chapter, we will talk about the mean, standard deviation, and the fit of a model, and we will define samples and populations. We will talk about null hypothesis and alternative hypothesis and confidence intervals. So we are in the last step of the research process, which is analyzing data. So whenever we try to analyze the data, we are trying to fit our model to real world data. So for example, the real world is this bridge, and we try to fit a model that can represent the data collected is known as the fit of the model. This is the degree to which a statistical model represents the data collected. It's known as the fit of the model. So we can have good fit, moderate fit, or poor fit. Population is defined as the collection of units to which we want to generalize a set of findings or a statistical model. Sample is a smaller collection of units from a population used to determine truth about that population. So remember, uh, we collect data from a small subset of the population known as a sample. And we use those data to infer things about the population as a whole. The bigger the sample, the more likely it is to reflect the whole population. It is almost impossible to work with the whole population. It is almost impossible to collect data from all people, from all plants, from all animals, from all cities. So we need to create a smaller portion of the whole population, and then we collect data from those units. And then by analyzing those data, we are trying to fit our sample into the population. We try to find the best fit of our model that represent the whole population. So this is the only equation you will ever need to remember. Outcome equals model plus error. As I said, we always have error. We always have measurement error. So the model can be as simple as the mean, or it can be complicated statistical tests like regression, ANOVA, t-test, correlation, and COVA, and the outcome is our dependent variable. So the simple statistical model is where we have mean as our model. So the mean is X bar, and we add up the all data points and then divide that by the number of data points. So mean is not a perfect representation of the data. Remember that, because if our data is skewed, the mean is not a best value representing our data. So this is a perfect fit, but this is not happening in the real world, unfortunately. So the blue horizontal line is the mean, and the yellow circles are each data points. And this is a perfect fit, which means there is no difference between actual values and the observed values. A deviation is a difference between the mean and actual data point. Deviations can be calculated by taking each score and subtracting the mean from it. So here, the black horizontal line is the mean, and those blue uh, dots are our data points. The red dashed lines are the differences between observed data points and the mean. So those uh, red dashed lines are errors. We can calculate the total error, but remember, total error always equals zero because deviations cancel out because some are positive and others are negative. So any data points above the mean are positive, any data points below the mean are negative. So those positive and negative values cancel out each other. That's why total error equals zero. That's why we can use other types of um, values like sum of squared errors. And that's the formula for sum of squared errors. Although the sum of squared errors is a good measure of the accuracy of our model, it depends on the amount of data collected. So in order to overcome this problem, we use mean squared error by dividing sum of squared error by degrees of freedom, which is n minus 1. Again, n is the number of data points. Degrees of freedom, BF, represent the number of values in a dataset that are free to vary when estimating a parameter. So in any sample, n is the number of observations, n is the number of sample size, n is the number of data points. N minus 1 is the degree of freedom. So for example, here, whenever the sample is 5, the degrees of freedom is 4. And whenever the sample is 4, the degrees of freedom is 3. And as I mentioned, large standard deviation means the data is more spread out. And the small standard deviation, it means the data points are clustered uh, in the center. We try to measure mean and standard deviation from our sample, and then our goal is to estimate the mean and standard deviation of the whole population. The confidence intervals is very important part of this module. We will see confidence intervals a lot. In every statistical test, we will have confidence interval. We need to report it in our results section in research articles. We can use the confidence interval to identify boundaries within which we believe the population will fall. So whenever we have the mean and we have the standard deviation, we can easily calculate confidence intervals. For a given statistic calculated for a sample of observations, for example, the mean, the confidence interval is a range of values around the mean that are believed to contain, with a certain probability, most of the time 95%, the true value of that statistic. So for example, here we have conditioned sperm release. The true mean of the population is 15 million. The sample mean is 17 million. The confidence interval estimate is 12 to 22 million. So it contains true value. But if our interval estimate is 16 to 18 million, it misses true value. So confidence intervals constructed such that 95% contain the true value. In order to display confidence interval, we can use an error bar. So the dots are the mean and the error bars are the confidence interval, which represent 95% of the data falls in that range. And we can use the letter I in order to display confidence interval. Regarding hypothesis, we can have null hypothesis, which means there is no effect, or alternative hypothesis, which means there is an effect. Remember, we have only one null hypothesis, but we can have multiple alternative hypotheses. The test statistic, so for example, t-test, regression, ANOVA, those are all test statistics. We are dividing the variance explained by the model by the variance not explained by the model. That's our test statistics. And as I mentioned, we can have one tail or two-tailed tests. If it is a one-tail test, it's called directional hypothesis. And whenever it is two-tail test, it's called non-directional hypothesis. Type 1 error and type 2 errors are very important. I'm gonna talk about this here. So let's say null hypothesis is true, but we reject null hypothesis. We commit type 1 error. It's also called alpha level. If null hypothesis is false and we reject null hypothesis, we are correct. If null hypothesis is true and we fail to reject null hypothesis, we are correct again. But if null hypothesis is false and we fail to reject null hypothesis, we commit type 2 error or beta level error. We can look at the confidence interval and get an idea about the statistical significance. So here on the right side, we have an example. We have sample 1 and sample 2, and we have confidence intervals, which is like the letter I. So remember, if there is no overlap between confidence intervals of two samples, we can be sure that our test statistic is significant, which means there is a significant um, difference between those two samples. But if there is a slight overlap between those two confidence intervals from two samples, that may or may not be significant. Remember that. What is the significance or purpose of reporting a frequency distribution statistic in published research? What do you think? So we need to report a frequency distribution for different reasons. First of all, it gives the reader the options to interpret our data. Secondly, it shows transparency of reporting everything. So frequency distribution gives the reader the idea about the distribution of our data points, um, the nature of our data points. So it is very crucial. It is very important to report a frequency distribution statistic. And I will ask you whenever we get to use PSS for different tests, I will ask you to report frequency distribution and report the kurtosis, skewness, and I will show you how to do that.